What happens when an unstoppable force meets an immovable object? What I mean by that, for example a cube, and it can't move, no moving around, okay? But then there's also an unstoppable force, which is like an arrow, I guess. If you haven't heard of the question, you should be ashamed of yourself, because even Jesus heard the question. Okay, I'm joking. So the answer to that question, heavily depends on what an unstoppable force is and what an immovable object is. So let's present a scenario, scenario 1. The force is a physical object, like a projectile. And that arrow has infinite momentum. It will not stop whatever you do. Now, if it collides with that immovable object, then the laws of physics are broken. If it collides, then that momentum must move the immovable cube, because it has infinite momentum and it should be able to move anything in its way. But we said that the cube is immovable, so that would also break the definition of the cube, because then the cube would be able to move. So that is not possible. We're gonna look in this video at multiple scenarios and see if the scenario is possible or not. Let's find out if there's a possible scenario. Also, if the projectile deforms or penetrates the cube, then the definition is also broken. And here we can also ask, what is the cube made out of? Or more specifically, do the atoms themselves also not move? I mean, they must not move, or else it wouldn't be an immovable cube. And then it couldn't penetrate the cube. Now let's look at the second scenario. In the second scenario, this is not an arrow. So if this is not an arrow, we're gonna say that force, that unstoppable force, is energy, like light or sound. And we can just look at light, for example. So light is a wave and a particle at the same time, and it's going right at the cube. Now think about a light wave. What happens if a light wave collides with an object? The object could reflect the light wave or absorb it into heat, for example. So now look at each of the two scenarios in here. If the light wave collides with the cube and the cube absorbs the light wave, then that also must break the cube's definition, because the cube is immovable. If the cube is made of atoms, which obviously that's the only way, and it absorbs the light wave, if a light wave gets absorbed by an object, the object is gonna heat up very slightly. Basically, the light wave collides with an atom in the cube. Atom is gonna be move and make the temperature rise. I'm oversimplifying here, but what do you expect of my drawings? If the light wave gets reflected, that question could be answered. The force gets reflected. But you know, it's boring and shit, you know. So how about it's not a light wave? Let's think about the force in a different way. What if the force is not a real natural force? Or maybe it is, but let's say the force is time or entropy. So time is unstoppable, right? It always moves forward. We can, near a black hole, like in Interstellar, speed up time for you if you're in a spaceship, but you can never stop time. So now the object battles against time, but the object doesn't care, you know. It's basically just a cube of atoms that can't be moved by any momentum. So by its definition, this could work, and they are actively colliding. They are always colliding. Time ages the physical reality, just moves forward and forward. It allows movement. Now with the scenario with time as the unstoppable force, we could also say the cube is a radioactive cube. So you know the half-life of radioactive isotopes. So these isotopes, they break down with time and they eject particles and stuff. So these isotopes in the cube, they decay and throw off alpha particles or gamma rays, beta. And now we can ask, if all of these isotopes decayed and the cube is gone, it just disintegrated into these rays, into energy, basically. So the cube isn't the same anymore. We changed the cube. We could say it has moved. So in certain scenarios, I think this would be fine in the question. This could be allowed per definition, but maybe with the isotopes it could also not be fine. It depends on how you look at it. Let's look at scenario 4. If the force is a concept, like an idea or law of nature. So you know, laws of physics are often considered unstoppable. They are always the same across the universe and they can't be stopped. You can't just change the laws of physics. So you might say the laws of physics are unstoppable. So if the immovable object is an absolute constant, it might resist change, but can it resist concepts? An example for that is if the cube is not a cube but a black hole. You could consider a black hole to be an immovable object for physical objects, but it still obeys gravity. If you take another black hole and put it next to it, excuse my bad drawings, they're gonna pull on each other. So the paradox depends on what level of existence we are considering. It depends on how deep we think and how much we are trying to wiggle the definitions to our likings so that it can be true. So we could say the paradox is more about definition than actual physics. If you think about it, the question was rigged from the start. There is no immovable object in the universe and there is no unstoppable force in the universe. There's always something that we can move or stop. Now we are not done yet. When we were talking about photons hitting the cube, we talked about absorption of the light wave, and I told you that it became heat. Now if you know some basic physics, you know that heat just means that atoms vibrate faster and faster if it's hotter and hotter. But if the cube is colder, then that just means that the atoms vibrate less. So you would think that at 0 degree Kelvin, the lowest temperature that could be literally zero, absolute zero, atoms don't move at all. Now logically that is true. But in reality, there are some quantum mechanics and stuff. So a perfect 0 Kelvin state can't exist because the atoms that vibrate are going to stay still in place. So they are not going to move, but that is not possible because of the Heisenberg uncertainty principle. Even at absolute zero, particles retain 0-point energy. That means that they still have some quantum fluctuations. We can never know the position of an electron because due to the Heisenberg uncertainty principle, they always just move around, so the atoms are going to vibrate nonetheless. We can mitigate it, we can slow it down as far as what have we reached? Something under 1 Kelvin probably, with some lasers hitting them, so that, well, the lasers hitting them in the opposite direction, so that it moves in the other direction, so that the atom doesn't move, so cancelling them out. But we can't reach 0 Kelvin. And now the same is true for the radioactive cube. The radioactive cube spits out energy in form of beta, gamma, delta, or no, in form of beta, gamma, alpha rays, and that would obviously prevent it from staying at absolute zero because the atoms would move. The energy emission raises temperature. Now we know that due to the quantum mechanics, quantum fluctuations, the cube cannot be immovable in the atomic sense or the quantum sense. But we could switch the definition that immovable means that the cube doesn't move in that macroscopic space. So that cube isn't going to spontaneously be here, right? That it's not going to move like that. But the atoms, I guess, because of the Heisenberg uncertainty principle and all the other ways that it can't be immovable, we know that this question is rigged from the start, from both points. But still, it's interesting to ask this question, am I right? So people, if you like this video, like and subscribe. Peace.